Hello everyone, welcome back to Alkaline Hydroxide 784. And today in the chemistry series, we will be covering the periodic table. I need to mentally prepare myself because I see like a more than a full page of stuff, and I don't want to take 1 hour to say everything. So let's just see how this goes. Okay, so yeah, let's go right into the learning outcomes. We have a lot to cover, I guess. The first thing, the trends and variations in atomic and physical properties. Right. So we're looking at third period, group 2 and group 17. So first one is the electronic configurations across a period and down a group. Once again, our best friend is the periodic table when it comes to chemistry. So, take your periodic table, look at it. You do realize that the electronic configuration is based on, like, can be inferred from the periodic table. So for the periodic table, you have the S block, the D block, the P block, and the F block below. And using that, you can try to figure out what is the electronic configuration. So like for example, if you have oxygen, you first have to see which period it is. Like oxygen is in the second period, right? So you wouldn't have any 3s or anything. It will be before 3s. And oxygen is in the P block, so you definitely be having a until 2p something, and it happens to be the fourth, like the fourth element in the P block. You know what I mean, like when you look at the arrangement, it's like the fourth one to the left, I guess, or to the right. I don't even know. When you're counting from left to right, the fourth one. That's why its electronic configuration is 1s2, 2s2, and 2p4. So that is how you figure out your electronic configuration. But of course, when you go to the D block area, especially the third period D block, you should remember the whole 4s fills up first before the 3D. So what you do when you actually see the D block, actually the periodic table helps with it because you see the 4s, like you see the S before the P. So yeah, cool. So if you look at the third period, it is the part with the 3s 3s2 3p6, right? And then after that, you see the next S is already the fourth like row kind of thing. So you use that to realize, okay, 4s fills up first, but the D section will be starting with 3, so you consider that as 3D. So you use that to count how much you're supposed to write down in the sense. Yeah. So that's the electronic configuration. That's how you do it. Of course, we saw some of the exceptions to the electronic configurations, which include especially when you're looking at the 4s 3D, that area there. If you are about to fill up all the 5d orbitals, either with single electrons or fill up all of them with double, like paired electrons, that would be preferred to having having 2 electrons in 4s, and the other, like, not having all 5 of them at the equal filling, in a sense, in the d orbital. Yeah. So just recognize that. So yeah, that's how it works. And for the next one, which is B, the next learning outcome in this section, we look at the general trends and variations. Oh wait, before we move on, since they did mention third period, group 2 and group 17, for third period, I think it's mostly just the sodium to chlorine bunch. I should probably open a periodic table. Wait a minute. Yeah, so so that part is very simple. It's just the usual S and P. And for group 2, it's going to all be S2, like whatever S2. And for group 17, it's gonna all be the atomic radius, ionic radius, i.e. electronegativity. Yeah, I think we already explained this last time, so I'm just gonna go through this really quickly. So I'll just try to remember what we have here. Atomic, ionic, i.e. and electronegativity. So we have across period and down a group. Okay, cool. So, okay, so for the first one, which is atomic, and the actual data that's in the book, we have this wonderful table called atomic and ionic radii. And if you see across a period, the atomic radii seems to, well, it seems to decrease until you get to the noble gases, and then it suddenly increases. Yeah, that's how it works, and I believe I explained why that happens, right? So when you add electrons to the same period, but the shell is still in the same distance away from the nucleus. So in a way, the electrons, okay, not same distance, as in the same outermost shell in the sense. So there's more electrons and there's more attraction, and the shielding effect is relatively constant, so the attraction is greater and the atomic radius decreases. Yeah, that's the idea here. Of course, down a group, you can see that for group 2, you can see in the table that it increases down the group, and that is because as you go down the group, there's more shells, so the electrons are further and are like on a more and more outermost shell, in the sense, like a bigger shell. So that shell is definitely gonna be further away from the nucleus, and there's lesser attraction in general. So it is to be expected that the atomic radius increases, yeah. And the shielding effect, even though it increases, the effect that is in the outer shell is more, it has more effect compared to the shielding effect. Yeah. So, right. So the next one will be the ionic radius. So for ionic radius, if you look at the table again, for the period, you would see that the ionic radius decreases for the cations, and then it suddenly increases and then decreases again for the anion. Yeah, so why does this happen? Well, if you look at so you just look at them together, like the same trend for both of them, as let's say for the cations, as you remove more and more electrons, you will have like they're all going to have the same electron shell, but since the electrons that you remove from them, what was I trying to say? Let me think. I was trying to remember why exactly it's like that. Like when you remove the electron from the outermost shell, obviously it will be lesser than its original atomic radius, but the reason why it decreases down the period as well is because removing the electrons from the same shell, in a way, makes it more and more positive. So the difference between the electrons and the nucleus charge will be increasing down the period if you're trying to make them all have the same shell, in a sense. So you can see lithium plus, beryllium 2 plus, boron 3 plus, and carbon 4 plus, which I think is super unlikely, but okay, we have it here. And it's more and more positive, so the attraction would be greater compared to when there's more electrons to balance out the charge in the sense. Yeah, I guess this is for the same number of electrons in all of them. So in that scenario, you would expect that the more positive nucleus, because there's more protons in carbon than in lithium, so obviously the attraction is going to be greater. Yeah, of course when you look at the normal atomic radius, the attraction is also greater, but it's just that there are actually electrons there as well too. Yeah, it's the same reasoning. Only thing is you put more emphasis on the positive part of the fact that it's positive. Okay, so for the anions, as you can see from C4 plus to C4 minus, you can see such a huge gap, like huge jump in radius. That's because you're adding electrons, so you increase the shell. And in that scenario, you would see that all of them have larger ionic radii than atomic radii, because once you add another shell, it's kind of like what happens when you go down the group, so it becomes bigger. And the reason why, let's say, fluorine minus is smaller than carbon 4 minus is because sorry, it's because the fluorine, like, it takes more and more energy to actually put electrons into, okay, yeah, and when you put more and more electrons, I think the repulsion is a bit greater. So for fluorine, you only need to put one electron, and fluorine has the most protons, so it actually has the most attraction to the electrons as well. So since for carbon it has lesser protons than fluorine, when you put 4 electrons into it, it's still going to have a lesser attraction compared to fluorine. So at the end of the day, it really is about the attraction of the nucleus, so how many protons there are to begin with. So even when you put the same number of electrons in everything, the protons do make a difference in the attraction. Right, so moving on. Yes. If you're looking at down a group instead, you look at group 2 and group 17. Down the group, you can see that it increases, the radii increases, and it's the same logic as what we saw in atomic radii. Only thing is just that their ionic radii are smaller than their atomic radii. Yeah, it's the same logic. So then for group 17, once again it's the same logic, only thing they're all minus, yeah, 1 electron. Like, by same logic, I mean the same logic as the atomic radii trend. So here the ionic radii is larger than the atomic radii, but it does increase down the group. So that's the idea. Okay, so the next one is what? Ionic energy. Yes, ionic energy. Sorry, ionization energy, not ionic energy. Of course, they mentioned the first ionization energy, and where you can actually see this information is in this beautiful table here called ionization energies. And they put the first, second, third, and fourth. Okay, cool. So if you look at period and group. So if you look at the period, you can take a look from let me see. From maybe potassium. Okay, actually you're supposed to get the third period. So from sodium to argon. So from sodium to argon, you can see the first IE increases a lot. Like, it keeps increasing. And of course, you know the reason for that. So yeah. We already covered why it increases in the previous episode, and that's because as the attraction is greater lah. We already know that the attraction increases. So when you try to remove an electron, you obviously will require more energy to remove an electron from something with more protons and more attraction to the electron, in a sense. Yeah. And the shielding effect is relatively same, so similar shielding effect, so it doesn't affect the increase in the ionization energy. And of course, as you can see, there's this thing with aluminium, where aluminium has a lower IE than magnesium, and silicon has a higher IE than both of them. So the discrepancy is between magnesium and aluminium, and it is the same as the discrepancy between beryllium and boron. So I think we also looked at that in a previous episode, and that is because from it is something to do with the S and the P, S to P transition. So even though the usual transition is viewed from each like from first, for example, from 2 2p to 3s or something like that, you can also view like big jumps, like you could view some smaller differences within the S and the P, like within the same principal quantum shell, in a sense, like the same, for example, from 2s to 2p, instead of simply from, for example, 2p to 3s or 3p to 3p to 4s, for example. You know what I mean? Yeah, that's like the smaller differences, and that's why aluminium has a smaller IE than magnesium, because it is in the p, it has one p electron, and that thing is alone, and it is slightly, there's a slight difference in the shielding effect for that particular part of it. Yeah, or at least it's a bit more repelled compared to all the s electrons, which are a bit more, intact in the sense. Okay, so if you're looking at electronegativity, electronegativity is not electron affinity, but instead the number, that the arbitrary number that they give 4 for like fluorine, and then they decrease the number through the on towards the other end of the periodic table. So in that scenario, electronegativity is more of how much it wants to attract the, electrons of other atoms and things like that. So electronegativity across a period increases because the, like, if you think about it from the viewpoint of IE, so IE is like how much energy you need to remove an electron. So it's easier to remove an electron on the left side. So electronegativity, you think about it the other way. Which one is the hardest to remove electron? It will be also the place where it's easiest to attract electrons. It wants the electrons the most. It would be on the right side of the periodic table towards the fluorine, halogens, and also oxygen, stuff like that. Yeah. But across the period, electronegativity increases because the number of protons increases, and the, yeah, it just has a stronger attraction within the same shell. Down a group, it decreases because the electrons are, like, the shell itself is so big. So if the shell itself becomes bigger and bigger, after a while the attraction for other electrons will also be lower, in a sense. There's a greater shielding effect in the sense, and that's why down a group the electronegativity decreases. Yeah, while across a period is about the same. Right, so yeah, so just use these points and refer to your notes as well, and then come up with a good explanation when you're asked to. So next point, next learning outcome is the variation in melting point and electrical conductivity across a period. Okay. Right. So this one is a bit more it's a bit different compared to the first few stuff that we already seen before in the previous chapters, I guess. So this one is about melting point and electrical conductivity. And you have to look at structure and bonding in the elements. So you're going to look at it across a period. So I'm going to look at period 3. Okay. And if you look at period 3, we have sodium on the leftmost and argon on the rightmost. As you can see, sodium, magnesium, aluminium are metals. Silicon is kind of like semiconductors, but it kind of looks metallic sometimes. Phosphorus is still can be solid in room temperature. Sulfur is, if actual sulfur is kind of solid actually. Chlorine and argon are gases at room temperature. So if you look at that, you realize that sodium, magnesium, aluminium are all partaking in metallic bonding. So in metallic bonding, you have a whole bunch of metal ions and a sea of delocalized electrons, and these bonds are quite strong, and that's what is keeping it together. So it's the metallic bonding that's keeping it together in terms of the melting or boiling point in a sense. Uh, yeah, that's why they have a very high melting point. It's about as simple as that. Okay. Then silicon, phosphorus, and sulfur. They have covalent bonding. If we're looking at the kind that we are familiar with, like silicon can form crystalline structures like carbon does. You know, carbon can form diamond, right? So diamond is really solid and nice. So likewise, silicon can also create crystalline structures. And phosphorus also has its own little covalent molecule, P4 I believe, and sulfur is S8. So they're all covalent molecules, and of course the phosphorus and sulfur still somewhat solid at room temperature, but they definitely have a lower melting point than the metal, because the covalent bonding isn't really the main factor in their, you know, inter like the attraction between the individual molecules. But silicon will have a decently high melting point, I believe, if it because it's kind of like covalent bonding between the individual silicon atoms. So yeah, so phosphorus and sulfur can be melted when once you blast it with some fire. So yeah. So their melting point isn't as high, but it's still not bad. You know, it's still okay. You can see them as solid at room temperature. Then chlorine and argon are definitely gases at room temperature, and of course that's because chlorine is, well, it's a chlorine 2. CO2 is the covalent bond is between the two Cl but not between the individual Cl2 molecules. And likewise, argon itself doesn't even form its own molecule, it's just argon, and they had to stay together with the help of van der Waals bonding instead of covalent bonding. Oh yeah, so in terms of covalent molecules, when you're looking at the bonding between the molecules, you'll be looking at something that's either like van der Waals, or of course if you're looking at pure elements, it's usually van der Waals, but maybe electrical compound, a different more of a compound kind of thing like water, then you can look at other things like polar or hydrogen bonding. Yeah. So van der Waals is also kind of known as instantaneous dipole induced dipole. So yeah, nothing much to say about that. So likewise, you can kind of tell how each of the different elements across the period, you know, like how they behave at certain temperatures. Yeah. Of course, the melting point down the group will increase because, as you can see, like the second period, nitrogen, oxygen, fluorine are all gases, but then the third period, phosphorus and sulfur are solid at room temperature. So as you can see, the melting point actually increases down the group because, you know, they all have that van der Waals bonding there, but that thing is stronger when you have more electrons in general. Yeah. So that the greater number of electrons allows for a more stronger transient dipole in a sense, because you have more chances of the electrons actually being unbalanced and creating a dipole. And you know what I mean. That makes sense. Yeah. So let's go back to the learning outcomes. Oh yes. And before we move on, we'll look at. They did mention something about metallic, giant molecular, or simple molecular. So when you're looking at the covalent structures, right, you should be a bit aware of which one it is. So if it's something like carbon or silicon, it is giant molecular, so it will have not simple molecular, because the bond that you need to break in order to melt it is actually covalent bonds, which are quite strong. A simple molecular would be the kind of smaller molecules like Cl2, O2, N2, or even phosphorus 4, sulfur 8 is not that big. It's only there's not that many molecules in it. So those rely more on van der Waals bonding. Yeah. Okay. Uh, the next one. Describe and explain the trend and volatility of the group 17 elements in terms of instantaneous dipole-induced dipole attraction. Yeah, this is the thing I was talking about. So obviously the group 17 elements, aka the halogens, it's basically the same as with other things, but for those specifically it is quite important because if you know iodine is not necessarily a gas, it is more of a liquid, and in fact if you move even further down you may actually see some solid. So it's possible, okay, actually iodine can be a solid at room temperature, so iodine itself can be a solid. But bromine is a liquid, I think. Bromine is liquid, iodine is a solid. Astatine is definitely a solid if you're looking at iodine being a solid. Fluorine and chlorine are gases. So if you look at that, then you realize that the melting point increases down the group 17, and that's because of what I mentioned just now. There's more electrons, more chance for IDID, and stronger IDID in general. Yeah, nothing much to say. But since it is IDID, they are quite volatile in the sense. Even if it's a liquid, bromine tends to fume like crazy. So that's an important thing to know. You should take care of yourself if you're handling bromine. Yeah. And even iodine tends to vaporize every now and then. So be careful. Right. Next one. Okay, finally you're moving to the next one. Trends and variations in chemical properties. So this will be specifically for the third period. And there's a whole bunch of stuff here. How fun. Okay, so you're gonna look at the oxides first. And chlorides. Oxides and chlorides. Oh my, this was like the hardest, this is like the most annoying topic to memorize because there's just so many trends to look at. Okay, now I remember that. Oh, I don't know if I can remember it now, but I'll try my best. Okay, state and explain the variation in the highest oxidation number for the elements in oxide and chlorides. Okay, so in oxides and chlorides, okay, this is more of oxidation number. So, yeah, for sodium it's 1, magnesium is 2, aluminium is 3, silicon is 4, phosphorus is 5. Okay, but in this, of course in oxide, phosphorus doesn't really do 5. It's more of like, let's say, there's 4 phosphorus to 10 oxygen. Okay, it is 5, yeah. Yeah, 5. And sulfur is 6. And this kind of correlates to how many electrons they have. Yeah, that makes sense. Well, like sodium only has 1 electron in its outermost shell. Magnesium has 2, aluminium has 3, silicon has 4, phosphorus has 5, and sulfur has 6. So it makes sense that they can afford to become that much positive and join with something that is negative, you know what I mean? Yeah. So that's just how it is. Yeah. So sodium can afford to lose 1 electron before it becomes a full orbital. So that's the point lah, that's the point. Like they can become that much positive before it becomes really hard to remove more electrons. Like the big jump in IE. That's why let's say if when you have the sulfur and oxygen. And I think it's also something to do with the fact that they're in the third period. So sulfur has 6. It can accommodate more because it is in the third period and it has access to the d orbitals above it, and it can therefore bring in more electrons. So it's actually not really positive per se, but more like it can accept a lot of electrons, and it has a lot of electrons of its own as well. Silicon dioxide is somewhat like carbon dioxide, so I think that's pretty obvious. Aluminium, magnesium, and sodium are all like positive thingies, so they're all ionic compounds, kind of. Aluminium oxide is probably less ionic, but it's also still an ionic compound. Silicon dioxide is a covalent compound. It's giant covalent, giant molecular for that matter. It's like diamond. It's actually quartz. Then P4O10 is actually not really giant per se, but it's a covalent compound. SO3 is definitely a simple molecular covalent compound. Yeah, nothing much to say. Okay, so for chlorides, it's the same logic. It's just 1, 2, 3, 4, 5. Of course, sulfur doesn't really have chlorine joining it because it would be too much, I guess. But you have NaCl, MgCl2, AlCl3. Actually, AlCl3 is a covalent compound, so I don't know how that happened. SiCl4 and PCl5. Of course, it's also dependent on how big their orbital can get. Yeah. So the 3D orbitals are tapped into eventually. Okay, so the next one, variation in bonding in oxides and chlorides in terms of electronegativity. Oh look, they even put with the exception of AlCO3 because AlCO3 is a covalent compound despite us thinking that it would be not a covalent compound. Okay, so electronegativity, you can see that the covalent compounds are the ones where there's a higher electronegativity. Okay, actually oxygen has a higher electronegativity than all of them. So maybe in this scenario it will be more of covalent compounds would be having a lower difference in electronegativity, whereas the ionic compounds will be having a higher difference in electronegativity. So that's the general idea. And likewise for the chlorides, except for AlCO3, for some reason it's covalent. Yeah. Okay, cool. Okay, so the next one is the reaction of the oxides with water. This is what I meant by the thing that I had so much trouble memorizing. The exact stuff that you say for the reaction. So let me just give disclaimer, I do not remember the exact description. So yeah. So Na2O or Na2O MgO Al2O3 SiO2 P4O10 and SO3. Okay, Na2O is going to be somewhat reactive, I believe, because you can form alkalines with that. I can form like NaOH and stuff like that. MgO will also be somewhat slightly lesser reactive, but it is still a bit reactive. Al2O3 also possible. SiO2 definitely not because it's like, I don't know, I just don't feel like it would actually dissolve in the water. Yeah, it has very strong covalent bonding. Because the ionic compounds can very easily dissociate in the water because the water will come and surround them, form those, what's that thing called, the I don't know, there's a name for that surrounding water molecule thing. Yeah. 10 and SO3 are simple covalent, so they will easily dissolve in water and become acids. Yeah. So please remember the equations and write them well. I know this is very troublesome to remember, so just try your best. Yeah. Oh yeah, okay, so for NaOH, MgOH2 and AlOH3, they will also do stuff in the water. Of course, you know what it looks like when you dissolve them in water. You've done it before, right? Right. Okay, so the final part of the same point is the apathetic behavior in reaction with sodium hydroxide. 3 is somewhat apathetic. So when you put it in sodium hydroxide, it doesn't do much useful stuff. And what am I trying to say? I know when you put like salt in the water and you're trying to put sodium hydroxide or something and see whether that particular thing will actually form a precipitate. Usually the zinc, aluminium and lead do not really form precipitate with the sodium hydroxide. And like, or even if they do form a precipitate, it dissolves somewhat readily, right? So in a sense, it's because of the apathetic behavior, and they can become, like, once you add a lot of the OH or the acid, it will form a complex, and you can use that to describe why it does that. Yeah. So look at your notes for more details in that, because I'm tired and it's already like 35 minutes. I don't want to talk for so long. But you get the idea. Let's talk about the fact that they form a complex, and write the equation very relevant. So actually I'm not sure if you're supposed to mention zinc. Okay, actually that one isn't really here, so we'll talk about that later on a different topic. Yeah. Anyways, the next point. Describe and explain the reactions of the chlorides with water. You know what? I don't want to talk about this anymore. Okay. Uh, yeah, NaCO doesn't do much. You know that, right? You put salt, nothing exciting happens. MgCl2, I think it becomes more and more dangerous, or at least more and more reactive as the further down, like the more right you go. Yeah, that's pretty much what happens. Just write the equations properly. Yeah. Okay, so you have to mention whether it forms an acid or not using your reaction as well. So do recognize that before you just anyhow write stuff. Okay, so type of structure and bonding present in oxides and chlorides. I think I already mentioned which one is ionic, which one is covalent, and you just use the information in the question if you're supposed to. Use that to explain why it will be ionic or covalent based on their melting point or something like that. Like the melting point is high, then it's likely to be an ionic compound, because the inter atomic or molecular bonding is actually ionic bonding, which is quite strong. Whereas if it's like a simple covalent compound, it would be something that has van der Waals in between the molecules. Yeah, so that's like I just say those things. You should be fine. Okay, so the final part of this is the elements in group 2 and group 17. You have to first look at the relative reactivity of them. Like group 2 is reducing agents, group 17 is oxidizing agents. Since they told us look at the E naught values, let me go and look, the standard E potential values in the sense. So if you look at the page here, okay, so there's one table with decreasing order of oxidizing power, and this will give you a selected number, and they're talking about whether how good the group 2 are at reducing and how good the group 17 are at oxidizing. So you'll look at the oxidizing power. So you can see at the very top, the topmost is the most oxidizing, is fluorine, and you can see it's in group 17, right? Fluorine is super oxidizing. Yay. And what's underneath fluorine? Chlorine. Chlorine has a lower value. Then next one will be bromine, which has lower value. Then iodine, which has lower value. And then they probably don't even care about S13. So yeah, you get the idea. So the group 17 elements down the group, it becomes less and less reduced less and less oxidizing, because, well, because, well, of course you do know that electronegativity decreases, right? So wait, what was I gonna say? I don't know what I was gonna say. So if like the electronegativity decreases, then the oxidizing ability also decreases. They're less reactive in general, because as the election, the reason is because down the group their the bonding is better, like there's a stronger bond in the sense. So since they have a stronger bond, they're less likely to just react with random stuff as it increase the number of protons and electrons in the individual elements. And for fluorine, it's really reactive, right? That's because its bond isn't particularly strong, so it's very easily attacks other things, given that it's quite electronegative. It's very interested to go and grab the electrons from somewhere else instead of itself, in a sense. Yeah. So that's why the oxidizing power decreases for group 17 down the group. If you're looking at group 2, let's see where group 2 is. Let's see, okay, let's start from potassium. Potassium is the most reducing, it is negative 2.92. And then if you go to okay, we're not, wait, sorry, not group, we're supposed to look at group 2, right? Oh shit, sorry, not group 1, group 2, sorry. Right, so calcium is the most reducing, negative 2.87. Next is magnesium, next is zinc, next is of course there is iron 2 plus, but it is not group 2, so let's ignore that. Next is no, I'm so distracted by all the transition metals, but you get the idea. It seems to become less and less reducing. So I guess it's the same reason, because but this is a different reasons. Okay, actually it's different. So like the electron, oh okay, wait, sorry, I just remembered something. The reason is actually supposed to do with the density of the charge or something like that. So for fluorine, like all of the halogens, right, they have the same -1 charge, but as the charge density kind of decreases down the group because it becomes bigger and bigger, right, the charge is the same. So for fluorine, it has a very high charge density, so that's why it is very reactive. And likewise for this one, of course the calcium will have the highest charge density out of the other group, all of the group 2 elements. Zinc isn't a group 2 element, I just realized, sorry. But whatever group 2 elements there are, so in a way the higher charge density will make it more reactive in general. Yeah. So that's the point. That was all I have to say. What's the next thing I had to say in what's the next learning outcome? Okay. So now we look at thermal stability. Right. Okay, so yeah, this is the same logic. It's something to do with the I actually just explain why it's like that, but for the part about the E naught values, right, you don't need to really explain why, but you need to say that, oh, the increasing for the group 17, right, since the values are decreasing, like it becomes less positive, so they are less oxidizing down the group. And for group 2, the values become less negative, so they are less reducing down the group. So that's basically that. So for the thermal stability part is whatever I mentioned just now, with the charge density being increasing or decreasing in the sense. But we're supposed to talk about another thing as well, because for the group 2 carbonates, you have to talk about the large anion. Okay, so actually it doesn't have to be carbonate, it can be another anion as well. So the idea is that of course the carbonate anion is quite a big electron cloud kind of thing, and it's quite polarizable because it is big and it has a lot of electrons to polarize. Of course the group 2 elements, as the charge density increases, in terms like the smaller it is, the higher charge density it has. So it kind of has a, you know like it polarizes the anion more, and it kind of makes the bonds within the anion weaker. And because the anion bonds are weakened, it's easier to decompose the particular anion into carbon dioxide. Yeah. So that's why the thermal stability kind of increases down the group, surprisingly or unsurprisingly or whatever, is because the anion itself is being weakened by the higher charge density. And for group 17, you're supposed to look at bond energies, and we know why the bond energy is varies down the group. If you want to look at the data, you can look at the bond energy, that data there. If you look at the heteronuclear one, the FCBRI, you can see the energy decreases, the bond energy is lower, and this is because we're looking at the in between the two of them. So you're not looking at intermolecular bonding, but within intramolecular bonding. So in this scenario, when you have a bigger and bigger halogen, the bigger electron cloud is like, what should I say? It just makes it harder for the hydrogen and the halogen to really form a proper bond sense. So the overlap, like the contact between the two of them, is lesser. Yeah. But if it's like a very small one like HF, it can really they can really be quite close and form a very strong bond between each other. So the idea here is about the electron, like the surface area that you can really contact is lesser in a sense. Yeah. Or the overlap is lesser because for this small little H thing and that big cloud, it's not matching it's not matching enough. So yeah, that's the main point. The point is that the electron cloud is bigger and the overlap in electrons is smaller, and therefore the bond energy, it doesn't attract as strongly. The bond energy isn't that strong. Okay, and because the bond energy decreases down the group, they're also less thermally stable down the group. So yeah, that's pretty much it. Okay, then the last bunch of stuff is characteristic properties of an element in a given group. You have to predict what the properties are. So basically, in a group, they all tend to have certain properties. Like for example, if you're looking at the alkali metals, which is group 1, you know that they tend to form alkalis in a sense, and like halogens, they all like to form in pairs and stuff like that, and noble gases just like to be alone. So you just use common sense and try to figure out what each of them is supposed to do. Yeah. Is there anything else? Okay, so the last one is the nature possible position in periodic table from the chemical and physical properties. So it's like the other way around. So you see the information and then you deduce what element it is from where exactly it is from the information. So it's the same thing but the other way around. So just use your common sense, use your periodic table very wisely, think about it carefully when you answer questions about the periodic table, and you'll be fine. I hope. As long as you don't get a question on the oxides and stuff like that, you should be fine. Yeah. Yeah, it's almost 50 minutes, so I'll probably wrap this up. I hope you found this video useful because I was talking for a very long time. I wasted my 50 minutes for this. Okay, not wasted, but I used up my 50 minutes for this, so it better be worthwhile. If you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye!